So good afternoon, Christos again, and good morning to colleagues from Europe, and good afternoon again to friends in India, Japan, Singapore. It's really my great pleasure to welcome you to this lecture of Professor Christos Panagopoulos. He's very, very well known in the field of fermions and quantum materials, and it's really nice of him that he accepted our kind invitation, and we are going to listen his great talk. And I'm sure to this audience, they know Christos very, very well, Christos. But I just give a very brief introduction about his biography. So Christos Panagopoulos was born in Australia, raised in Greece, Australia and Japan, and educated in all the three countries and in Britain, so really international education and career. He received his PhD from University of Cambridge in the Trinity College in 1997. He has since held positions as Trinity College Research Fellow and Royal Society University Research Fellow at the University of Cambridge, European Excellence Grant, and then European Young Investigator Awardee, and Professor of Physics at the University of Crete in Greece. He is currently the inaugural University Research Professor at the Nanyang Technological University and investigator of the National Research Foundation, the Prime Minister's office in Singapore. Meanwhile, he served at the Naval Academy in Athens, received education on the business of science at Imperial College in London, and raised over 40 million euros through competitive research grants. Really a lot of money for science. He started and co-developed the condensed matter section at Nanyang Technological University, chaired many panels on research and education, and served as reviewer on strategic initiatives for research centers in North America, Asia, and Europe. He has taught many undergraduate and graduate courses in physics, educated and trained numerous researchers and technical staff, published more than 140 research articles in condensed matter physics, delivered many keynote speeches and over 200 invited presentations at conferences and universities. For his research, he develops materials and experimental techniques to connect the quantum architecture of materials directly with the new device responses. So again, many thanks, Christos, for accepting our invitation. On behalf of my team, Dr. Brajbhushan Singh, Puspendra Shakti, and others, I welcome you all. And I also like to mention that during the lecture, we don't take any questions. So dear participants, if you have any questions, you can kindly write in the chat box or just say I have a question. At the end, we will take all the questions one by one. So Christos, it's all yours. Looking forward to your kind lecture. Thank you.
Thank you very much. Thank you for the nice introduction and the invitation. If you cannot hear me, please let me know now.
Yes.
Great. So let me start. I'll just put it on the right. So the idea of today's talk is to introduce you to a project that we started a few years back, and it's to work on quantum hybrids. So today I will focus on one particular aim, which is a way to couple materials using topological defects, for instance, solitons. And through that, we want to be able to engineer magnetism and superconducting order parameters. So to guide you through, what do I mean by solitons? I will look into first I will start with the classical solitons just to remind our mind. The classical solitons, as we know, they are solutions to non-linear field equations with finite energy density and non-dissipative confinement to a finite spatial region. And a typical example one can find in nature is shallow water waves. Now, unlike classical solitons, we also have topological solitons, and there is a review which, or actually a long discussion that if you're interested to look at with, which I wrote with a colleague of mine, Alex Bogdanov, this year and last year, where we discuss classical and topological solitons. But essentially, they are just like classical solitons, but they also cannot be trivially mapped onto the ground state. And they carry non-zero topological charge in some cases. And they modify their local environment after passing through. And examples of topological solitons are quite wide in nature. For instance, you can see this in Sine-Gordon-Kings, the Skyr model for mesons and baryons, but also topological defects in the early universe, in superconductors, in magnets, in ferroelectrics, and many more. Now, today I would like to focus on two types of systems where we can have topological solitons, and these would be superconductors and magnets, so for the sake of today's discussion. In the case of topological solitons and superconductors, the first thing that one appreciates is the Abrikosov vortices. These were discussed for the first time in 1957 by Alexei Abrikosov in the former Soviet Union, and they're essentially topological soliton solutions to the Ginzburg-Landau equations, describing the order parameter psi and a supercurrent density Js, supercurrent Js. Now, the beauty of these Abrikosov vortices and why they are important for today's discussion is that they are characterized by 2n pi phase winding around the core, where psi, where the order parameter that is, and here is a typical vortex core down here, would go to 0. And this leads to flux quantization. They're also stabilized by negative surface energy between superconducting and normal states for as long as the ratio of the penetration depth, lambda, shown here, to the coherence length psi is greater than 1/√2. So here is a nice typical image of the vortices from top, and this is a side view of the sample as the magnetic field goes through the sample, the superconductor. And the critical parameters are essentially the order parameter, which goes to 0 at the center of the core, the magnetic penetration depth, which is the region over which the field penetrates, and the coherence length, which is approximately half of the size of this vortex. Now, it was only 30 years later, or one can say it took 30 years, until someone, and in particular Bogdanov and Yablonsky, also in the Soviet Union, postulated that vortex-like states, similar to the superconductors, could actually develop in magnetic materials. And here is a schematic or a sketch of what a vortex, magnetic vortex, may look like and be topologically protected. And they came up with the suggestion that this could be actually magnetic skyrmions, right? Essentially, what this means really in physics is that they are particle-like spin worlds with nanoscale dimensions, just a few nanometers wide. They have a non-zero integer topological charge, and they are actually stabilized by competition between spin-rotating Jaroszynski-Moriya interaction, which I will mention later, and spin-aligning magnetic exchange and anisotropy. And these are the forces essentially that stabilize these magnetic textures in a vortex form. Now, both superconducting vortices and magnetic skyrmions have been discussed over the years in terms of applications, and this is the technological impulse actually for looking at these systems. For instance, all the way back to 1960s, superconducting vortices were proposed for cryogenic memory. And magnetic vortices, such as skyrmions, have also been suggested more recently for racetrack operations. Similar, there have been analogs to memory and artificial synapses proposals for neuromorphic computing using skyrmions, but also one can consider the possibility of having controllable beam deflection and lensing in liquid crystals. What we find particularly exciting, and I would like to say a few words today, is that one may actually use these magnetic skyrmions or these magnetic textures to induce local changes in the superconducting pairing symmetry. And this is especially useful and important because one can use this possibility for hardware in quantum information. Now, why would this be? Because the possibility of having localized Majorana zero modes with skyrmions has already been discussed, and it has been a subject for the past 5 to 10 years of intense investigation. Now, if you have an even winding number in skyrmions, such as n equals 2, for instance, it has been suggested that one could actually look for a radial spin flip that could have localizing Majorana zero modes. There is a problem here in practice is that they are unstable in chiral magnets. Another possibility for localizing Majorana zero modes with skyrmions is to use bimerons. These are essentially stretched skyrmions, such as shown here. And here is a bimeron, for example. The problem with having a bimeron to be utilized for localizing Majorana zero modes is that they require a complex device geometry in order to braid. The other possibility is to use a winding number n equals 1 and have skyrmion vortex pairs. So here, if n plus m, where m is in the case for the skyrmion, for the vortex, and n equals 1, then if the sum is even, that would give you Majoranas that would emerge at the skyrmion core and at the system rim. So the question is, can we actually practically stabilize skyrmion vortex pairs? In other words, can we have a system or develop a system that you can have both superconducting vortices and magnetic skyrmions to coexist? Now, this at first sounds probably impossible, because usually magnetism and superconductivity don't go together, let alone to have them coupled across a sample. But if you are able to engineer this and you find the right physical parameters to do so, then there is a hope that this is actually doable. Now, and this is important because it can lead to topological superconductivity in a platform that you can actually manipulate, that is engineer. And that means you can create topological superconductivity from combining Zeeman splitting, spin-orbit coupling, and S-wave pairing. So in real space, what you will have is non-collinear magnetic order, which is gauge equivalent to having Zeeman plus spin-orbit coupling. And therefore, by imprinting non-collinear magnet onto an S-wave superconductor would give you a two-dimensional skyrmion configuration forming dispersive Majorana edge states and localized Majorana fermions within the vortex cores. And there have been several theoretical mechanisms testing this idea, and they all point to the direction that indeed, if one is able ever to imprint a non-collinear magnet onto an S-wave superconductor, that then in principle, there should be actually the presence of Majorana fermions within the vortex cores of this system. And there have been several papers already, theoretical articles in the past 6 years. So the major challenge is really to have a superconductor magnet hybrid, and therefore develop a platform in order to host and manipulate quasi-particles which can be useful in quantum computing. And here the stray magnetic field, for instance, from the skyrmion, would induce vortices in the superconductor. And these skyrmion vortex pairs may be the ones to host stable hybrid topological excitations. But having such hybrids is also very useful for being able to have magnetoelectric tuning. So for instance, if you can see on the schematic on the right-hand side, if you have the superconducting vortices and the skyrmions being coupled, then this skyrmion vortex coupling could become a magnetoelectric handle to control spin flux. For instance, you could use this to move skyrmions at a certain velocity by a spin current through spin transfer torque or spin Hall effect, or a thermal gradient inducing a perpendicular voltage, or vice versa to drive skyrmion flow, for example. But also you can use AC vortex motion to probe magnetic resonance and spin wave and Cherenkov-Magnon radiation above a certain critical flux velocity. These are all proposals that have been actually put out there over the past decade, but still there had not been a system that could actually couple the skyrmions to the magnet, to the superconductor. Another idea that has been proposed in such a system is you can have a disordered periodic pinit potential simulator, which would be ideal to study granular flow in complex environments, such as jamming, tailgating, avalanches, etc., including in earth science studies. But also one would expect in such a case to have a typical skyrmion vortex density of up to 10 to the 7 per millimeter square and induce ultrafast in the order of kilometer per second particle motion. And all these proposals have been put out there, and indeed there has been some experimental efforts to date in order to look at the possibility of coupling magnets with skyrmions or either chiral textures, but locally, that is, have topological connection between a chiral magnetic texture and a superconducting vortex. But so far, there hadn't been a possibility of actually having the presence of both superconducting vortices and magnetic skyrmions within the same system. most of it would be either one or the other. So the challenge that we actually faced a few years ago and we put to ourselves was to identify a system with stable skimions below the superconducting transition temperature and below the upper critical field of the superconductor. That is where you can accommodate superconducting vortices. So our bilayer concept essentially is drawn here. We have a dirty type 2 film, that is, you have a high upper critical, superconducting upper critical field, and you put this on top of on a thin film multilayer, which has a high Jałodziński-Morilla and a large tunable magnetic moment. And the first thing you need to do is to clarify the interaction between the superconducting vortices in your superconductor and the skimions in your chiral magnet. The first actual interaction that you need to consider is the Rush-Byeldestein exchange coupling. That is essentially a superconducting magnetoelectric effect. So if you have a skimion in a ferromagnet sitting above a vortex of a superconductor, shown here in the schematic, then spin polarization will generate a supercurrent. And that supercurrent will be a function of spin-orbit coupling and the skimion exchange field. So a superposition of supercurrent on vortex currents would cause a skimion-vortex interaction. Now, the interaction or the nature of this interaction would be controlled by the vorticity and the skimion helicity. And if this is negative, that would be an attractive interaction. If it is positive, it would be a repulsive interaction. So if spin-orbit coupling, skimion exchange field, or the skimion radius are sufficiently large, then the supercurrent would allow skimions to generate Abrikosov vortices. Now, the second interaction mechanism or coupling mechanism is stray field coupling. Here, the interaction is determined by the vorticity relative to the skimion core polarity. So if you are to increase the radius of your magnetic skimion or your magnetic vortex and the saturation magnetization MS, that would give rise to a stronger coupling. So a larger skimion, a larger magnetic vortex, or a higher saturation magnetization in your magnet would give rise to a spontaneous vortex or anti-vortex pair formation. A small size magnetic skimion or magnetic vortex, or a small saturation magnetization in your magnet would allow for a Meissner screening. And a topological band structure would remain robust in the skimion stray field. So the stray field coupling would be ubiquitous. And Rush-Byeldestein coupling can in fact be switched off, therefore, by an insulating spacer between your superconductor and your ferromagnet. So if I am to match the skimion or the magnetic vortex with the superconducting vortex, then I would need to match the length scales. So if I want to have exchange coupling, then the skimion-induced current must spatially coincide with the vortex current in order to reduce the free energy of the superconductor. And therefore, it would be inappropriate to have a skimion whose radius is smaller than the coherence length of the superconductor, or a skimion whose radius is larger than the magnetic penetration depth in the superconductor. For stray field coupling, you need to make the radius of your skimion as large as possible. And therefore, in the thin film limit, the vortices would form for as long as the product of the thickness of your superconductor with your magnet with the saturation magnetization and the size of the skimion is greater than the parameters shown here, and I will return to these numbers later. So you need to satisfy these two coupling mechanisms by tuning the size of your skimion and the size of the magnetic penetration depth and the superconducting coherence length in your superconductor. So you need to devise a system that you can simultaneously optimize the superconducting and the magnetic parameters in order to maximize the skimion vortex coupling between your superconductor and your ferromagnet. So the first task is to design the multilayer, the magnetic multilayer. Now we know that if you have a magnet, a standard system, then the reason that you can have spin alignment is because there is a good balance between Zeeman, exchange, and anisotropy. If I am to add a heavy metal next to this magnet, then I induce a so-called Jaroszynski-Moriya interaction, which is the cross product of the spins next to each other, I and J. And this would give rise to spin winding in my ferromagnet. So this is how a domain wall or a spin winding would look like near the interface of this bilayer of a heavy metal to a magnet. Now, therefore, what this says is that the interface between a ferromagnet and a heavy metal would give rise to a broken inversion symmetry, and the spin-orbit coupling of the heavy metal would mediate this Jaroszynski-Moriya interaction in the magnet, which will allow you to have spin canting in the radial plane at this interface. So remember, at this stage, I'm not working with my superconductor at all. I am trying to figure out how to design the right magnetic multilayer in order to deposit on it my superconductor. And this magnetic multilayer needs to have the right ingredients in order to induce or to stabilize skyrmions that are of the right size that would make sense to coupling to the vortices. So having this interfacial or multilayer magnet would give me the right spin canting in the radial plane, but in 2 dimensions, this canting would give rise to so-called nail skyrmions. And these nail skyrmions have been around since 2013, actually. The problem back in 2013 is that they only occurred at very low temperatures. So in order to have them at multiple temperatures, which is what we want, you need to tune the thickness of your magnet or to tune the number of interfaces. So you need to consider tunable stack repeats of this ferromagnet with your spin-orbit coupling interfaces. And this is something that my former postdoc, who just moved recently to Johns Hopkins, Raju, came up actually back in 2016. So the idea is that if you exchange couple the ferromagnet and the spin-orbit coupling, that would increase the effective magnetic TC without affecting the interfacial Jaroszynski-Moriya. And you would achieve a high TC for your skyrmions and a non-zero Jaroszynski-Moriya interaction. So in other words, you should be able not only to have these skyrmions at a wider temperature range, that is even up to room temperature, as we showed eventually, but also to tune their size and density by changing the stacks. And indeed, by having additive Jaroszynski-Moriya interacting vectors from platinum, cobalt, and iridium iron, then you can actually change the effective Jaroszynski-Moriya vector. And that allows you to have tunability. You can tune the effective Jaroszynski-Moriya, you can tune the exchange anisotropy, uniaxial anisotropy, and all this by changing the thickness of your iron cobalt layers in your heterostructure. But also you can see here, by changing this thickness, then you can change not only the size of your skyrmions, but also the density. So now we are ready, and we know that this is the system that we need in order to play with, in order to couple to a superconductor. Also, we are able to show convincingly, and this is again one of my former students, Bartendo, who just moved actually this month to the University of California. So he was able to show that these are indeed nail skyrmions. So what you see on the left-hand side is the magnetization, and you can see the center of mass of the normalized skyrmion magnetization rotating counterclockwise. And on the right-hand side, you see the topological density, and that is because due to the momentum conservation, the center of mass of the topological charge density of these skyrmions remains static, but its maximum rotates also counterclockwise. So now we know that not only we can create these magnetic textures, but they are rotating counterclockwise and they are nail skyrmions. Also, you can have more tunability by changing the stack repetition, that is N. And this modulates again the uniaxial anisotropy and the saturation magnetization of your multilayer. So going through many materials and many trials, we were able to select this particular sample for the discussion with the superconductor that I will continue from now on. So we select iridium 1, iron 0.5, cobalt 0.5, platinum 1, and we have 10 repeats. And this gives us the optimal balance between the skyrmion stability, the skyrmion presence range, and the skyrmion stray field amplitude, which we need if we are to couple or induce superconducting vortices. So Cohen, who graduated last year, was able to find a very beautiful way of characterizing skyrmions from bulk magnetization. So here on the right-hand side, what Cohen was able to show many times is that there is a tiny region of magnetization as a function of magnetic field where you observe a little hysteresis. And in this hysteresis is where you have this beautiful skyrmion formation that I discussed before. At higher fields, it saturates to a ferromagnet. At lower fields, you have magnetic stripes. So this is another beautiful way of identifying, even without doing ferromagnetic resonance that Bartender did in order to study the nail skyrmions, or doing some other studies. And there are other methods as well that you can look how the skyrmions nucleate as a function of magnetic field and temperature. And if you want to find more about this topological Hall effect, which is affected directly from the presence of magnetic skyrmions, you can read Raju's paper, which was published just a couple of months ago. So having selected the right heterostructure for our study, we are able now to identify the skyrmions in more detail and measure those and find that the specific material that we are interested in would have the right size of skyrmions. And in particular, for this material shown here, we have a radius which is approximately 47 nanometers at 5 degrees Kelvin and below. So the next thing is to match the superconducting layer to this value. And this is work that actually was done between my two researchers, Alex Petrovich and Raju. So they worked very hard together in order to get the right parameters and build the right samples so that they work. Now you have to understand when you develop this superconducting layer is that the Meissner screening becomes weaker in thin film superconductors. And therefore you have greater flux penetration. So if you have a film which, let's say its thickness is ds and it's smaller than the magnetic penetration depth in the superconductor, then you have to replace the magnetic penetration depth with a Pearl length, which is capital Greek lambda. And therefore here you would expect that the coherence length, the superconducting coherence length, would be suppressed by defects in the thin film because you are in the dirty limit. So what you need to do then is you need to vary the superconducting film thickness ds in order to match the coherence length and the magnetic penetration depth with the size of your magnetic skyrmion. And with that, after a lot of effort and trial and error, we were able to select niobium films with a thickness of 25 nanometers. And from Ginzburg-Landau analysis, both of resistivity and magnetization, we calculated or we estimated the superconducting coherence length to be roughly 10 nanometers, and the Pearl length to be approximately 200 nanometers as we approach 0 Kelvin. On the right-hand side, you see magnetotransport data from our niobium films. Note that these niobium films, because they are so thin, they are capped with a very thin platinum, which I will touch upon soon. And by looking at the data here, the upper critical field, it indicates that indeed we are in the two-dimensional limit. Now, as I mentioned, there is a platinum, what I call platinum caveat. And that is because there is a proximity-induced expansion of the coherence length. These platinum layers protect against oxidation, but at the same time, because you have this 2 nanometers platinum on top of your superconductor, then you have an effective coherence length which is larger than the pure superconducting coherence length of your system. And in order to calculate this, or in order to measure this, you need to actually have a local imaging method of the effective coherence length so that you can evaluate the skyrmion vortex coupling. And to do that, we have used a home-built scanning tunneling microscope. So we measure down to at 400 millikelvin, and as you can see here, these are typical images of the superconducting vortices in our niobium platinum. And we can calculate, or we can actually measure from here, the effective superconducting coherence length in our niobium film capped with platinum. And it turns out to be approximately 36 nanometers. Indeed, a little bit higher than the pure niobium. So now we can have the final recipe for our heterostructure. You can see the first one has exchange plus stray field coupling. Why? That is because now in this heterostructure, we touch directly our superconductor, that is our niobium, on our chiral magnet, the material that I mentioned earlier, which is platinum, cobalt, iron, iridium, 10 repeats. The other material that we will have is one with stray field coupling. That is because we inserted an insulator, specifically magnesium oxide, between the superconductor and the chiral magnet. I will call the one which is superconductor chiral magnet MS for magnet superconductor, and the other one superconductor insulator chiral magnet MIS for magnet insulator superconductor. And by measuring the coherence length, the Pearl length, and the skyrmion radius directly with our imaging techniques, we know that our skyrmion radius is 47 nanometers, and it is between the effective coherence length and the Pearl length, precisely as we want it based on theoretical estimates in order to have coupling between vortices and skyrmions. And for reference, we have our standard niobium film with the 2 nanometer platinum on top, our superconductor. So the first measurement to do is a bulk magnetization in order to see whether indeed the skyrmions are affecting the magnetic vortices and vice versa. On the top row, you will see data for the MS system, and the bottom row is for the MIS system. On the left-hand side, the left column, is the total magnetization. The middle column is just the magnet on its own, and the right column is the difference, that is the superconducting component. Now note, and I would like to mention this, is that the determination of the coherence length or the temperature dependence of the superconducting coherence length from the magnetization data is consistent with the transport data, despite the fact that the hysteresis loop is inverted relative to textbook type 2 superconductors. And this inversion is purely because of the inhomogeneity in the magnetometer. But what is important to realize is that we will now focus on the first magnetization quadrant, shown here in the pink square, as we go from above the skyrmion nucleation field to 0. Let me actually pause for a moment to remind you what do I mean by skyrmion nucleation field. Skyrmion nucleation field is the magnetic field below which we start seeing the emergence of magnetic skyrmions, and above which we have just saturation and a beautiful ferromagnet. So we will focus on this behavior as we go down here. And we will be looking at the superconducting component, which is the right-hand side column. So by looking at this quadrant, we see a deviation from the saturation magnetization downwards, which I point here in green circles for the MS and the MIS sample. And for reference and comparison, I'll show you the behavior of the pure superconductor shown here as S. What you observe immediately is 3 points. First, the superconducting component of the magnetization in our heterostructure turns increasingly negative below the skyrmion nucleation field, shown here in the green circle. And that indicates the formation of anti-vortices and vortex exposure. Also, there is a stronger anti-vortex response in the MS films compared to the MIS films. There is a larger drop in the magnetization of the superconducting component. And finally, there is vortex spinning enhancement at very low magnetic fields, as you can see here. So what is the quantitative justification for anti-vortex formation due to the presence of magnetic skyrmions in the heterostructure? Anti-vortex formation is derived from the following principles. First, stray field of the anti-vortex must change the skyrmion radius. And the total free energy of your system after the formation of anti-vortices must be lower than the free energy without an anti-vortex present. So therefore, one can write an inequality and define a threshold for anti-vortex formation. And this is precisely what Eremin's group in Germany did in this article by Dahir et al. And they calculated the threshold for block skyrmions, and I will come back to this, nucleating vortex-anti-vortex pairs in zero field to be 1.36 Tesla. So, for skyrmion stray field exceeding the lower critical field in the superconductor, one would have a saturation magnetization, which is relatively high. And indeed, in our case, is 1.82 Tesla, with an HC1 being only 0.012 Tesla. So we satisfy this. The skyrmion flux should exceed phi naught half of the vortices. And indeed, if you model the skyrmion as two Néel domain walls, then the skyrmion flux would be 4.5 times phi naught. So that satisfies the anti-vortex formation due to the presence of skyrmions in our heterostructures. And finally, Eremin's condition for anti-vortex nucleation is for the saturation magnetization to be 1.36 Tesla at least. And in our case, our saturation magnetization is 1.82 Tesla, which is much higher than that. But remember, this is for block textures. And I mentioned before that we have shown through Bartendu's work that we have Néel skyrmions. So if you want to have a rigorous proof of anti-vortex nucleation in our heterostructures, or at all with Néel skyrmions, you should consider a realistic Néel stray field profile, finite separation between chiral magnetic and superconducting fields, and a finite thickness of the superconductor. And in order to do that and be absolutely certain, we combine micromagnetic model of skyrmion stray field with Ginzburg-Landau simulations of the superconducting response. And we do the calculations. So for the micromagnetic simulations of our heterostructure, we perform Newmax, and we find that indeed we can calculate a radius of a skyrmion to be 46 nanometers. This is exactly, well, almost the same with the 47 nanometers that we measured from magnetic imaging in our samples. So, and we can initialize relaxation of with MFM imaged magnetization, and through these micromagnetic simulations, we can also calculate the bulk magnetization. And in the center, you can see the simulations in pink agreeing very well with the experiment shown in black curve. So it looks like our simulations can reproduce our magnetic heterostructure and the magnetic texture configuration as a function of magnetic field very well. So having this confidence, we can now calculate the skyrmion flux. And it turns out for the MS heterostructure to be minus 1.5 phi naught. Whereas for the MIS heterostructure, where the superconductor is separated from the magnet by an insulator, is minus 1.1 phi naught in the superconducting plane. And this indicates the presence of anti-vortex formation, just as we expected from the quantitative calculations. The next thing we do is we combine the skyrmion stray field with homogeneous external field in order to obtain the magnetic vertex potential, vector potential. Then we apply time-dependent Ginzburg-Landau theory, and from here we can calculate the spatially dependent order parameter for the superconductor. And we can solve for this order parameter and therefore determine the supercurrent density in our superconductor, JS. And this is the result shown in this schematic, which is the calculation. So what you find is that skyrmions, shown here in blue color, nucleate anti-vortices, shown also in blue, in the superconductor. Now, the superconductor is on top, and your magnet, your multilayer, is on the bottom. So this magnetic blue skyrmion nucleates anti-vortices inside your superconductor on the top. And these anti-vortices coexist with superconducting vortices in the superconductor, shown here in red, parallel to the magnetic field. Now, note that the gray screening currents, which are at a distance or a radius, which is approximately the radius of your magnetic skyrmion inside the multilayer, these are the ones that ensure anti-vortex stability. So you can immediately see the formation of skyrmion anti-vortex pairs, and they're actually connected energetically. just as we anticipated through the connection. And you can do more. Now you can look at the field-dependent anti-vortex density. So what I show you here in the top row is the stray field coming out from the magnetic layer. And I go from the left to right with increasing the magnetic field. And in the bottom, I show you the magnetic response of the superconductor, again, going with increasing magnetic field from left to right. And what you find is that the anti-vortex population inside your superconductor, that is these blue circles, increases as you go from the skyrmion nucleation field towards zero field, and shown here in this plot. Also, you find this anti-vortex density is higher in the MS heterostructures. And that is understandable because the stray field is larger, because the niobium layer in the MS heterostructure is much closer to the magnet. There is no insulator in between. So, having actually confirmed that we indeed have created skyrmions and superconductors and superconducting antivortexes being connected, we can look at the flux dynamics of the superconductor in the presence of these spin topological defects, so-called skyrmions. And for this, we deposited niobium platinum wires on a very large millimeter scale heterostructure with skyrmions and measured IV characteristics. And you find that the critical current density in my superconducting skyrmion hybrid rises below the skyrmion nucleation field. And this enhancement in the critical current density vanishes at the skyrmion annihilation field. So in other words, what this tells you is that these topological spin textures pin fluxons. And if you do the reverse field sweep, then the same holds true. And you can explore the critical current density and the changes in the magnetization of your superconductor using time-dependent Ginzburg-Landau simulations. And by doing so, we can simulate the dynamics of the condensate and the flux driven by the external applied current density. And what you see here from this plot, you find that the vortices, which are parallel to the magnetic field, follow a percolative path through the sample. You also have these antivortices remaining above the skyrmions or magnetic stripes or magnetic domain walls, where the magnetization is antiparallel to the applied field. And finally, the skyrmion stripe screening currents block the vortex flow. So you can see that there is a direct correlation and effect of the skyrmion presence above the superconducting vortices and antivortices. In fact, you can look at this into some more detail, and what you find is that vortices and antivortices in your superconductor move in opposite directions. And the vortex-antivortex attraction weakens the vortex screening current repulsion. And therefore, you observe vortex-antivortex annihilation at the skyrmion edge. Also, you have new vortex-antivortex pairs being spontaneously nucleated on opposite sides of a skyrmion, and the presence of antivortices facilitates flux flow inside your superconductor. And this explains why there is a lower critical current density in MS fields. That is because there is a stronger stray field creating a higher antivortex density. You can look at also what I mentioned earlier, that in principle there is some theory or theoretical work years ago which were predicting that vortex rivers and high current density in the presence of coupling between superconducting vortices and antivortices with magnetic skyrmions would increase the speed or the velocities of vortices in the superconductor. Indeed, what we find is that vortices tailgate to form rivers with ultra-fast flow velocities. In fact, the velocities of these rivers in the superconductor go to kilometers per second, which is really fast. And the tailgating reduces the effective viscosity of the Cooper pair, the superconducting pair medium. And it is the skyrmions actually that provide the necessary spatial inhomogeneity, which is essential for this river formation in the vortex dynamics, as you can see here. So you can engineer not only the velocity, but also the path of your vortices in your superconductor with the topology of the magnet just above it. Notably, the anti-vortices also preserve stable flux flow. What we see here is in the IV characteristics that I have plotted in the middle, in the MS and MIS samples. When you look into the details in the circled areas, there is a high resistive flux flow at intermediate films, especially in the MS films. And the flow instabilities show clearly in the MIS films. You can see these very beautiful jumps, voltage jumps, signaling the breakdown of superconductivity. And there is a flux flow stability where the threshold velocity, as I mentioned earlier, is kilometers per second at low fields. So the story so far is that stray field dominates in our heterostructures. In other words, there is anti-vortex nucleation in your superconductor by having skyrmions and helical spin stripes above it through the multilayer. And the anti-vortex density in your superconductor can be controlled also with temperature, which I didn't have time to mention, but also with magnetic field. And there is enhanced flash spinning by stray magnetic fields coming from your chiral textures towards your superconductor. Moreover, we were able to show that this vortex-anti-vortex attraction facilitates flux flow across spinning barriers. So all the above can be explained and modeled, as I mentioned earlier, by stray field coupling between your magnet and your superconductor. The question now arising is that are there also signatures of Rush-by-Edelstein exchange coupling in this heterostructure? So in other words, can we detect Rush-by-Edelstein coupling in our structure or at all? Right, so in order to detect this, you need to align the peak vortex screening current at a radius which is approximately 2 times the superconducting coherence length. And the peak at the Rush-by-Edelstein current at a distance which is approximately the radius of your skyrmion should be such that you have maximal coupling. Now, we find from our magnetic force microscopy measurements, when we look at our magnetic skyrmions, that as I go closer to the nucleation field, the skyrmions tend to become a little bit larger. Actually, I mentioned our skyrmions are approximately 43 or 45 nanometers in radius. When I get closer to the nucleation field, they grow to approximately 60 nanometers. So if I am to look for Rush-by-Edelstein coupling, then I should be looking at skyrmions in the presence of a magnetic field which is near the nucleation field. And that's what we did. And indeed, what we find is that when we look at the critical current density of our heterostructure, there is an enhancement in the critical current, which begins at fields which are higher when you have exchange coupling. And the magnetization kink, which indicates anti-vortex nucleation, exhibits a similar behavior. So that points to the fact that indeed, when I have the right size of skyrmions, and I am close to my superconductor, then I do have Rush-by-Edelstein exchange coupling. So we can track the temperature dependence of the field where the superconducting component of the magnetization first responds to skyrmion formation. And for this, with this, we can actually look at where exactly Rush-by-Edelstein coupling switches on or switches off. So what we find is that the Rush-by-Edelstein coupling is indeed enhanced. In other words, the field where the superconductor responds for the first time to the formation of skyrmions rises as the effective superconducting coherence length drops in the MS films. Whereas there is no Rush-by-Edelstein coupling when I insert an insulator and I decouple my superconductor from my magnet. And you can see here that the field where the superconductor first responds to the nucleation of skyrmions drops due to the rise in the critical field, the lower critical field of the superconductor as I lower the temperature. And there is a weaker thermal fluctuation and therefore suppressing the skyrmion nucleation field. So in brief, At low temperature, rush by Edelstein and anti-vortex currents interfere constructively, and this enhances anti-vortex formation. Whereas at high temperatures, the 2 psi effective, that is the effective superconducting coherence length in my superconductor with my platinum, grows much larger than the size of the skyrmion. And therefore, rush by Edelstein currents and anti-vortex currents flow in different spatial locations. And therefore, this rush by Edelstein coupling is suppressed. So to summarize, I have shown you that we have finally been successful in developing, for the first time, a host of skyrmion anti-vortex pairs, where you can have magnetic skyrmions in the magnetic multilayer coupling to a superconductor and creating this energy string of 2 topological defects with different order parameters, one magnetic and one superconducting. And this is, as I mentioned earlier, based on theory, and one has to look at it from now on, a prerequisite for localized Majorana zero modes. And for this work, which was published again only this year, I would like to thank first my group at NTU, primarily Alex Petrovich and Raju, for actually working very closely together in order to develop the right platform and the very careful measurements, especially of Alex Petrovich, together with Xiangyang Ti and Koan Duong for this project. But it would not have been possible without the very close collaboration in the past few years with our collaborators at Technion in Israel, primarily Misha and Alex, in Geneva, Ivan and Christos, and also in Belgium, in Antwerp, for a lot of the simulations that was done by the group of Milorad Milosevic. And you for listening to this talk. Thank you.
Okay, thank you so much, Christos, for this excellent overview of your recent endeavors. On behalf of our team and our participants, I clap for your excellent lecture.
Thank you.
Thank you so much. So now the talk is open for questions. I don't see right now any, so I may start. I have actually a few questions. The coupling between the vortex and the skyrmions. So this physics is very interesting, but I think it is kind of limited with respect to temperature, because it's basically governed by the superconductor what you are taking.
Right.
So do you think like we can take this high TC superconductor for this kind of physics?
Right. So in fact, the main limiting parameter is not, I wouldn't say temperature, but is the superconducting parameters. In other words, you need to match the superconducting coherence length and the superconducting magnetic penetration depth to the size of your skyrmion. Having, indeed, as you correctly said, superconductor used here has a low transition temperature. It's only a few degrees Kelvin. But nothing stops you from having a higher temperature superconductor for as long as you can also stabilize skyrmions at high temperature. Now, our platform, skyrmion platform, can actually have skyrmions all the way up to room temperature. This is the work that we showed for the first time when Anjan was actually my postdoc here back in 2017, 2016 with Raju. So that is not a problem. The superconductor, yes, indeed, you should be able to get a high temperature superconductor, or not necessarily an oxide, could be other superconductors, and do that for as long as you can have the right size of coherence length.
Okay.
But this is the first proof of concept.
Okay, thank you. One more question from my side. So when you put this coupling of skyrmions and vortex or anti-vortex, what is the behavior in terms of velocity? So do you see any enhancement? Because that is one of the major challenges for based applications, isn't it?
Right. So at this stage, we have only looked at the dynamics of the superconducting anti-vortices and vortices. And as I mentioned earlier, they are significantly enhanced in kilometers per second, one of the fastest ever, actually. We haven't looked at the skyrmions, but indeed, what we do see, however, is that the skyrmion motion is affected, but we haven't looked at that. So this is yet to be done.
Okay, thank you so much. I see there is somebody raised hand, AM. So please unmute and ask.
Hi, this is Ashish. Sorry, ANM, so that is a class 3. I have one question. It's a very nice talk, by the way. It's very informative and new direction. And you can hear me, right?
Yes, I can hear you.
Yeah. So in this case, once you have the superconductor on this topological, this fermion, do you see that is there any possibility to have a Shiva state and create Shiva state or Majorana modes there
Right.
in this case?
So the prediction is that you should have Majorana modes, and one of the experiments that one would like to do, and we are also trying, is to look inside the vortex with STM. There is a challenge, as I showed you earlier, that you have this platinum on top in order to avoid oxidation. But ideally, and it's doable, if you have the platinum or any other, if you have the niobium on top of your skyrmion and vice versa, you can look at the core of your superconducting vortex or anti-vortex and look for possibility of Majorana modes in the zero bias anomaly. But there are also other methods that one can actually try, transport methods that we are trying to develop. So the long story short, or the long answer short, is that this is precisely the purpose of this exercise, is to have a platform where you can actually look for localized Majorana zero modes. And now that the platform is available, one can indeed employ different techniques to look for.
Sorry, I have another one that what happens is, suppose, can you just comment on that whether if I replace this fermion with Meron pair or the half fermion or the anti-fermions, do you think that there will be certain behavioral change or certain new things come there?
If you were to change to bimeron, for instance, there would be some different effect. It won't be as clear as it is with just a skyrmion, put it that way. If you were to have an anti-skyrmion, then you have to play with symmetry parameters. And then without elaborating, I would just say, consider that you have a different sign of a topological charge, how you would be able to interpret what I said before. But nothing precludes you from doing that.
Okay, thank you.
Okay, thanks, Christos, for answering those questions. Is there any other question from anyone?
Yes, sir, I have one question.
Yeah, please.
Nice talk, Christos. So I want to just ask, how did you measure chiral magnetic moment? Because you have written microjoule per Tesla.
So this is estimate from for a magnetic resonance and together with simulations.
Okay, so
we have a certain different methods, and not all of them are direct. So we do simulations, we do also transport measurements, magnetization measurements, and also imaging as well, which we try to fit very often with calculations or micromagnetic simulations in order to get quantitative estimates.
Okay, thanks. So, I would like to use this platform to understand this one. I have seen your one paper on arXiv where you used ferromagnetic resonance to identify skyrmion phases, but I don't know, is this published paper or not?
Yes, the paper appeared in Nature Communications last month. I think I have the reference here. If you bear with me, let me guide you to the reference. It is shown here, if you can.
Oh, okay. So how is the reliability of the ferromagnetic resonance to detect skyrmion phase? I mean, if we are not looking for other direct technique like magnetic force microscopy, can we rely only on FMR?
No, we do a combinatorial method. And in fact, this article of Bartendo, this Nature Communications, is the first ever ferromagnetic resonance in multi-layers hosting chiral textures and skyrmions. And what we show there is that ferromagnetic resonance measurements, either as a function of field or as a function of frequency, coupled with analytical theory and micromagnetic simulations, can actually identify the details of the different textures across a wide frequency range in a complex multi-layer system. And also it can identify not only the magnitudes, but also spatial orientations.
Okay, thank you.
So may I suggest that actually, if you have time to look at this article, and where all the details are there.
No,
And
no,
in fact,
I will, because I have read your archive one, but I will read this one. This is published now. Yeah, thank you.
You're welcome.
Okay, thanks, Braj. Thanks, Christos. Is there any more question? If not the case, then Christos, I'd like to present you a small plaque from our organizing team. So if you could stop sharing, then I would like to share my screen.
Stop share. Thank you.
Okay, I share my screen. Do you see my screen?
Oh, thank you. Yes, I see.
All
Very
right.
nice.
So, on behalf of our team, WTS seminar, webinar series on spintronics, National Institute of Science, Education and Research, Mysore, Bhubaneswar, India, takes pleasure in presenting this plaque to Professor Christos Panagopoulos from Nanyang Technological University, Singapore, in recognition and appreciation for being a valuable speaker to give a lecture on coupling topological solitons in hybrid quantum architectures. So it's a many thanks from all of us for giving this wonderful lecture and connecting to us in this difficult time. I hope we meet sometime soon in person, and that would be really nice, and to welcome you in our institute and to listen your talk, maybe in a larger audience.
Indeed.
So thank you so much, Christos. Please stay safe and stay healthy, and I wish you all good health, and see you next week in the seminar WTS by Professor Shashi Satpathy from University of Missouri. Different time because it's US. Okay, thank you so
very much.
Bye-bye, and see you next time. Thank
See you
you.
later. Bye-bye.
Bye-bye.
Thank you.